Before we zoom into individual blocks, fix one idea in your mind. A GPU is not built to run one thing fast. It is built to run thousands of things efficiently, even when memory is slow. Every structure you're about to see exists to hide latency, maximize throughput, and keep execution moving forward. Think of this chip as a throughput machine, not a fast single core. When one operation waits, another instantly takes its place. Performance comes from overlap, not speed. HBM is external high bandwidth DRAM connected to the GPU. It provides massive bandwidth but high latency. So programmers need to use coalesced memory access to get the best performance. We'll revisit this topic in future videos for a deeper look. Memory requests are merged, aligned, and reordered here. Well-structured access patterns turn bandwidth into performance. Poor patterns silently waste it. GPU kernels cannot directly read from PCIe. All PCIe transfers are controlled by the host or runtime. Kernels must access data already in device memory, HBM, or rely on unified memory to trigger automatic migration. The GigaThread Engine schedules thousands of threads across all SMs, keeping the GPU busy and hiding memory latency. With MIG control, a GPU can be partitioned into independent instances, letting multiple workloads run safely and efficiently. We'll explore this in more detail in future videos. High-speed GPU to GPU communication removes the CPU from the critical path, enabling true multi-GPU scaling. This cache automatically reduces repeated global memory access. You cannot control it directly, but coalesced accesses and reuse patterns improve efficiency. This is the coordination point that prevents memory, compute, and I/O from blocking each other under heavy load. For now, note this graphics processing cluster pattern. We'll explore it next. GPUs scale by replication. More clusters run more work in parallel, not faster threads. This is a streaming multiprocessor, SM. It runs independently within its graphics processing cluster. We'll expand and have a deeper look. Grouping execution engines balances workload and resource usage without programmer intervention. This is the smallest unit you directly program against. Every CUDA decision, block size, shared memory usage, registers, occupancy, ultimately determines how well this single engine stays busy. This L1 instruction cache stores upcoming instructions so threads don't have to wait. It keeps the SM running smoothly, even for kernels with many branches. These small local caches store instructions close to the threads. They reduce delays when different threads take different branches. All memory requests go through this pipeline. Threads that access memory in order are fast, while scattered accesses slow things down. Complex math is offloaded here, so general pipelines remain available for other work. This unit moves large chunks of data in the background, so computation can continue without waiting. This is the GPU's shared memory, a small programmable memory space for threads in a block. Proper use lets threads cooperate efficiently, speeding up computation. Misuse or conflicts can dramatically slow performance. These units, originally dedicated to graphics texturing, now serve as hardware accelerators for predictable, spatially coherent memory access patterns frequently generated by AI kernels. This is the warp scheduler. It issues instructions from groups of threads called warps. If one warp waits for data, it quickly switches to another to keep the SM busy. The dispatch unit routes instructions to available execution units, making sure the GPU stays fully utilized. This is the register file, storing each thread's private variables on chip. Keeping data here avoids slow memory access, but the limited size restricts how many threads can run at the same time. The integer unit handles 32-bit calculations, like addresses and branch decisions, so threads know where to read, write, and which instructions to follow. The FP32 unit performs 32-bit floating point calculations, handling most numerical work in kernels. It is designed for high throughput, keeping many threads busy rather than finishing one calculation as fast as possible. The FP64 unit handles 64-bit floating point calculations for high precision work. It is slower than FP32, so use it only when needed to avoid reducing throughput. These units trade flexibility for extreme efficiency, accelerating dense math by orders of magnitude. Write code that feeds the machine continuously, avoids unnecessary synchronization, and respects the hardware. When you do, the GPU will reward you with massive, predictable performance.